you're welcome back to my YouTube channel. Today I'll be dealing with a question that relates the dipole moment to the electric force, and I want you to follow along. Question: determine the force on a 3.0 coulomb charge placed 5.0 meter from the midpoint of a dipole moment 4.0 coulomb centimeter and separation 0.2 meter on a line perpendicular to the dipole. So we consider the solution. For you to accurately solve this question, you have to implement a diagram. So we'll go back to the question: determine the force on a 3.0 coulomb charge. Let's imagine that this is the charge placed somewhere here, 3.0 coulomb Q. Now we say it is placed 5.0 meter from the midpoint of a dipole of moment. So let's relate it. That's 5.0 meter away from the midpoint of a dipole. Let's imagine that this is a dipole, the positive pole here, Q, and the negative pole here. So imagine that that is the dipole. Now this is the midpoint. Definitely it's placed 5.0 meter from the midpoint. Now, and we're told that the dipole moment around here, which we can tag as P, is 4.0 coulomb centimeter. That is definitely, dipole moment is a product of charge and distance. That's why you're having coulomb centimeter here, which could be coulomb meter. Let's just follow along. And separation, that is, the poles are separated by a distance of 0.2 meter. Definitely this will be 0.1 meter, and this other part will be 0.1 meter on a line perpendicular to the dipole. Definitely this distance is perpendicular to the dipole. We have interpreted the question accurately, but there are some things we need to complete on this diagram. The distance between this particular charge now and the positive pole Q and plus Q is going to be through this line, while the distance between these two is going to be through this other line. So if we are going to calculate, determine the force, the total force relating here, there's going to be a F1 here between these two and a F2 between these two. So the resultant is going to be the total force. So now, in order to calculate F1, if you recall, our formula is going to be K modular of Q, then modular of the positive pole over R square. If we relate where we have Q 3.0, we don't have positive value for positive Q. We'll calculate that very soon. We don't also have the value for R square. Let's now go into calculating the value for positive Q and R square. The value for positive Q is also going to be the value for negative Q. Why? Because it's a dipole, the equal charges, but different polarity. So now let's go. How do we calculate it? We calculate it from this formula we wrote before. Dipole moment, which is given, is equal to the charge times distance. So definitely the charge we are looking for is going to be equal to the dipole moment given over D. Dipole moment given is 4.0 coulomb centimeter over the distance between the two poles is 0.2 meter. 0.2 meter. Our calculation for Q will now be 4.0 coulomb centimeter over 0.2 meter is going to be times 100 to express it in centimeter. So now that will now be 4.0 coulomb centimeter over, definitely this is going to be 20 centimeter. Centimeter will cancel as centimeter. Be left with something of this sort, 1 over 5, which is 1 over 5 coulomb, which is 0.2 coulomb. So that is the charge. Definitely that is what plus Q and minus Q we take. They are going to take this. So that means plus Q and minus Q have the actual charge of 0.2 coulomb. So let's now go back to calculating the first force. The first force K, Q, and then plus Q over R square. So there's something we are yet to find. If you look at, go back to this diagram, look at the R bit here. You can call that R1, but it's actually going to be the same as R2. Why? Because this is same and this is same. But notwithstanding, let's just call it R1 to take it step by step solving. And this other distance, let's call it what? R2. So R1, R2. So in order to resolve R1, we bring out this triangle. So to bring out that triangle, we have something of this sort. This is R1 we are looking at. Here is 0.1 meter. Here we have 5 meter. Definitely, if you use Pythagoras theorem, you know that R1 square equal to 5 square plus 0.1 square. R1 square will now be what? 25. So that you have 25.01 meter square. So definitely we can now find F1 K Q plus Q over R square. Definitely K, as we all know, 9 times from my previous lectures, 9 times 10 raised to power 9. Then Q, that was where we started from, that this Q, this is 3.0 column 3. Then plus Q, recall that, so that will be 0.2 all over R1 square. So because this is R1 now, you understand, R1 square will find it to be 25.01. so if you resolve all of this, you'd obtain 0.22 Newton settled. So now the same goes for F2. F2 this time around is going to be the relationship between this Q, that is this very guy, and this one now, this time around, the negative polarity over, we can say this R2. So now we know this, R2, let's resolve R2 the other way around. See it, that other triangle. So this was the 0.1 meter, this is the 5 meter, this is R2. So definitely still Pythagoras will apply here. R2 square will be equal to 5 what square plus 0.1 square. That will still give you 25.01 meter square. So now we can now go to resolve F2 K Q negative Q over R2 square. That will give you 9 times 10 raised to power 9 times 3 times, this remains 0.2 over 25.01. Definitely 25.01. You remember, please, we didn't do square root, so that's why we are leaving this, you understand, R2 square. So we left it, we didn't do square root, so you cannot come here and add square again, since we left it in the square format in the initially when we were solving. So please just get that straight. So the total here will still give you the same thing, 0.22 Newton. The difference between F1 and F2 remains the fact that F1 is going to definitely be repulsive, because this is positive and this is positive. You understand? This is positive and this is positive. Why this is going to be attractive? This is a positive and this is a negative. So they are not actually different in magnitude, but just in the way they will, act. So the total force is not going to just be F1 plus F2, but we are going to consider the diagram again. We had F1 here and we had F2 here. We had Q here. We had the distance to this point. And we recall that minus Q was here, positive Q was here. So if we call this F, let's call this one F positive now, and call this F negative. Instead of the net force being F1 plus F2, it's going to be F positive plus F negative. Why? Because in this case, it was not just a straight linear relationship. There was a inclination, an angle involved. And if we consider this very angle, we'll still be getting the same answer as when we consider this angle theta 2. It's just that in this case, you are going to use sine. In this case, you are going to use cos. In this case, if you use sine, that's opposite over what? Hypotenuse. Now in this case, if you use cos, adjacent over what? Hypotenuse. So let's go with one of that. Same here, theta 1. And call this theta 2. Now let's go with theta 1. So we have a situation where sine theta 1 equals to opposite F plus. Why are we doing this? We are doing this so that we can find out what F plus is. F plus over hypotenuse. That's F1. So at the end of the day, we can see F plus is what? F1 sine theta 1. So we already know F1, but we don't know what sine theta 1 is. We can get sine theta 1 by recalling that this very point was 0.1 in the diagram, and this one we calculated this r, this long r here to be r will be square root of what, 25.01, and we could recall that this from here to here was r. So definitely sine theta 1 now will be opposite 0.1 over square root of what, 25.01. So that's going to give you 0.02. So in this case now, f plus, we can say f plus is f1 times 0.02. f1, which we have calculated, was 0.22, now times 0.02. So that will give us 0.0044. That settles f plus. Now if we now go to doing something similar for f minus, if you look at this, if we use sine here, sine theta 1 will still be what, this opposite over what, this. So let's put that down. Sine theta 1 is going to be opposite of sine theta 1 is f minus over hypotenuse, f2. So now while we're doing this, we're looking for f minus. F minus will now be f2 sine theta 1. We have already found sine theta 1. We know f2 already, 0.22. Sine theta 1 is 0.02. We found sine theta 1 here. Then we already have f2. So when you multiply, you have 0.0044 Newton. So the total force, instead of being f1 plus f2, now it's going to be f plus f minus. Please, these are just symbols. You can represent them in your own way too. You understand? Instead of saying f plus, you can use any other thing. You understand? So that this is not what confuses you. Just get the essential point. Now this very one we have calculated this to be 0.0044 plus 0.0044. Why is this quite different from what the last question we did? Because in the place of a direct relationship, maybe linearly, you see in the last question we did, there was a linear relationship. This time there is an angle, so we know how to resolve in case of an angle. That's why we're looking at something like this. So at the end of the day, we have 0.0088 Newton, and that can be expressed in standard form as 8.8 times 10 to the power minus 3 Newton. That settles it. Thank you for watching. Do endeavor to subscribe to my YouTube channel. Thank you.